Have the chat up. It's pretty easy to upload. And it's not a switch light, it's a standard switch. Let's see, I'll put this on this side so I can read any comments that come in through there. Oh, enable streamer mode, that's always good. Okay. It's 5:02 and we are streaming, so let's begin. All right. Module 4. We are a fourth of the way through the course. This acts more of a part 2 in our talk of cryptography. This section does get away from the lower level, which would be everything that we saw last week of like XOR and different math functions and that kind of stuff. This is more of the implementation of the math. So as always, I got a picture. And this week is that because this is super secure. Haha. Haha. Please don't store your keys that way. I did not take this picture. Found this online like I did most of my pictures. So as a quick refresher of Module 3, anything cryptographically misconfigured is a vulnerability that attackers know how to exploit. If you enable cryptography on an application that you're building, on an infrastructure that you're setting up, whatever the case may be, if you do not configure it properly, that will be your biggest vulnerability. Your first line of defense is your key strength, the resiliency of keys to an attack. Taking this key, for example, because it is so easy to spot, it would be easy to take the key and make a copy. That is not strong key resiliency. The other thing that you want with your cryptographic configuration is that your keys should also be random. The more unpredictable the pattern, the stronger the key. Of course, you also want keys to be long. The shorter they are, the easier they are to break. And also the length of time for which the key is used. Limiting the time that you use a key will bring down the chances that that key can get compromised. Another point is please do not use secret algorithms or ones that haven't been tested in the wild. You really want to use cryptographic algorithms and cryptographic functions that already exist because those have been tried and tested. Those are better than making a custom. Now with that, implementing cryptography, here's 2 examples of implementing cryptography. The first one is ECB, the electronic code book. This is a basic approach, taking plain text, dividing it in blocks, and each block is encrypted separately. What you end up with is two identical plain text blocks into identical ciphertext blocks that you can do cryptanalysis to decrypt the message. ECB is not considered safe for use. Whereas CBC, the cipher block chaining, is a common cipher mode. It takes ciphertext blocks and feeds them back into the encryption process to encrypt the next block, basically like an XOR. As you can see in this picture, this is the difference between ECB and CBC. By taking a cipher block and using that block to encrypt the next block and to encrypt the next block, we make what is completely unrecognizable from the original. Whereas taking each block and encrypting it separately will result in something that we can see what's happening. Modern operating systems, like the current version of Windows, Mac, and Linux, they all have built-in services to handle cryptography, just like printing or just like networking, USB, and so on. There is a cryptographic service. If you look at the Windows services, you'll see it there. In inputting information into an algorithm, in order to make that stronger, so just because we put in password does not make that strong. We need to add more to it. For example, we need to add a salt, basically a random piece of information that will make the same hash different every single time. Windows does not do this. Mac and Linux do. If you're on a Windows box, know that your password is not added. There's no salt added to it, so it is easy to figure out. There's also a nonce, a unique value within a scope. So, for example, it'll be used for a given period, like a session. There's also initialization vectors, or IVs. These tend to be used more in wireless. So like I said, it is possible to take a password from Windows and figure out what it is. I, for whatever reason, mistakenly put this wrong. It starts with 88. Password in Windows starts with 88 and ends with 6C. I have it right in the lecture notes. You can test it yourself. If you make a username or a user and you set a password of password with the result being starting with 88 and ending with 6C, you'll be able to verify that it is the same by using this tool called Mimikatz. Now, I was going to do a live demonstration, but as if you are well aware of presentations, live demos don't always work right. So I was able to do it ahead of time, and I took snapshots of the process. If you are interested in seeing that this is true, here's an example for you to copy later on. So step one, on GCP, I created a server. It is a standard Windows server with desktop experience, server 2019, actually. As you should always, you set the Windows password and then log into the RDP system. So far, so good. Pretty standard, just like you did when you set up your Windows VM. For me, the password was this. Now, by any other standard, this is a secure password. Well, I used CyberChef to tell me what the NTLM, the way that Windows saves passwords, I was able to recreate it by using encoding text in UTF-16LE and MD4. This is the exact same process that Windows does when you enter a password and it saves it as a hash. This is the hash. If you don't believe me, keep watching. So first thing I had to do after logging on and ensuring my password, I had to disable the antivirus. I went into PowerShell. So right from the start menu, you have PowerShell. I right-clicked PowerShell and chose Run as Administrator. I got that lovely UAC that said, do I really want to do this? Of course, I said yes. And you're presented with this. If you are administrator and you see the folder that you're working in, System32, you're in the right place. This is the command you need to uninstall Windows Defender. That whole line, uninstall -Windows feature -name Windows Defender. It'll take a while. And then when it's done, it'll tell you this, that it was successful and you need to restart. So you go ahead and restart the system. Now we're going to download and run the tool. On my lecture notes, I have the link on where to go to download Mimikatz. And that's where it's at. That's what the page looks like. You want to get the latest version as of this recording today. 2.2.0 is the latest version of Mimikatz. So you want to download the zip file, the mimikatz_trunk.zip. And then we need to make our way back to PowerShell, because remember what we did earlier is we uninstalled Windows Defender and we rebooted the server. So now that we're back in the server, we need to reopen up PowerShell the same way you just did earlier as administrator. With this link, I right-clicked it and copied the location. Then I did these commands. Because I am running from System32, I changed to my username. So when you do this yourself, change directory in PowerShell to your profile. Then I typed invoke web request space, and then I right-clicked and it pasted the link that I got from the site, and I outputted, this is a capital O, to a zip called mimi.zip. When that was done, then I ran in PowerShell this command to unzip the archive. Then I went into the x64 folder because that's the version of Windows that we're working with. And I ran Mimikatz with start process mimikatz.exe. Within Mimikatz, now that it's running, I ran these two commands, the privilege debug, and I got a 20 OK, cool. And then I ran this other command to bring out the password. This is the result. So I took the picture from CyberChef at the beginning of this example, and I put it with the output that I got from Mimikatz. The NTLM hash is exactly the same. This is not good. You should not be able to use a free site and in 2 steps be able to figure out the hash for any possible Windows password. And this is exactly what an adversary would do. All you have to do is have a library of all these hashes and you can figure out whatever password they're using. Here's your Windows example. have fun trying that on your own system and screaming at the top of your lungs when you realize that it's that easy. Moving on to digital certificates, another implementation of cryptography. Digital certificates are like a government issued ID or a school issued ID. It is a way of verifying who you are. A digital certificate is used to associate a user identity to a public key that has been signed by a third party. A government issued ID has been signed by the government. That is the third party. Otherwise, how do you know I am who I say I am? As with a physical ID card, you'll have things like the signature, a serial number, expiration date, that kind of stuff. With a certificate, we have various authorities. For example, a certificate signing request can be something like a car title application. When you affix a public key to the certificate, that's when you sign the car title. An intermediate certificate authority could be something like visiting the county courthouse. Getting the actual title itself for the car is like the certificate authority. The DMV issues titles. They're the ones responsible for the certificates. You can go to a courthouse to process something on behalf of the DMV. This is the same function that we use for these digital certificates in order to ensure that they are real and they're verified. Managing our certificates is of great importance. So this certificate repository that you can bring up in Windows, for example, will show you any expired certificates that it knows. And it'll add them to this list, the certificate revocation list. You can also get these, the online certificate status protocol, or OSCP. We use this in our browsers all the time. It's a real-time lookup for certificates, kind of like DNS. Typically, this is also called the request response protocol. It's OSCP stapling is just another way to get responses, these responses for our browser during the handshake, to again verify that you are going to Amazon and you're not going to Amazon.com with a 0 instead of an O. We do have different types of certificates. We have the root certificate, and then we have intermediates along the way, and then the users. You kind of see here as an example of how these certificates build up a hierarchy. So Equifax would be the main holder of the certificate, and then we have these other entities to be intermediates, with buyonline.com having a user certificate that is backed by all these entities. We typically see certificates in HTTPS communication. That's the closest that you use it on a daily basis. This picture shows you what has to happen in the background when our browser goes to a site that is HTTPS and has to go through this process in order to get a certificate, verify it, and secure the communication between the server and the browser. And this all happens in a blink of an eye. the formats for these can be like privacy enhancement mail or PEM, personal information exchange or PFX files, or PKCS number 12. It's one of 15 standards defined by RSA. So in order to manage these certificates, we have different models to trust. The very first one is a hierarchical, where we have one root certificate authority that has a single key. This obviously is not ideal, because if the one box is compromised, all the certificates are now worthless. We have distributed, where we have multiple certificate authorities that can sign certificates. This builds some redundancy. If the main CA is lost, we're okay because we have some intermediates to stand in place. This also allows our CAs to respond faster because they can load balance. There's also bridged, where we have two separate root certificate authorities, but they are interconnected, so they can certify each other's certificates. Again, being able to handle multiple connections, multiple requests and responses by spreading the load across many systems. Certificates should not last forever. They should be created and die after a certain point. You should not expect to use the same certificate over and over again. This is in order to keep any adversaries from figuring out the certificate and forging their own and causing impersonation mayhem by having a exact copy of the private key. If you are creating certificates, you want to ensure that you're replacing them. Let's Encrypt, for example, gives you 90-day certificate. So every 3 months, you have to recreate another. And they make it very easy. With just a command, you can renew your cert. Now, public keys are stored within the certificate, but the private keys are on local systems. When you have multiple keys, you need to have a way to handle who has access to what. In this example, 3 parts of a key are distributed to 6 people, with 2 having the same part. The N group is the one who has 3 parts. The M group has the other 3. If a piece of the key is lost, stolen, corrupted, the key can be recreated. No one person has the full key, the full private key to open this cert, but these 6 people can come together. 3 of the 6 can come together to make the private key in order to generate a new certificate. This ensures that no one person has too much power. Now, again, last week was deep in the math, so quote. This is more of the application. So where do you see cryptography at work? Well, you see it with things like SSL. You see it with TLS, who is the replacement of SSL. You see it in secure shell. that uses port 22. You see HTTPS, who uses port 443. You see it in SMIME for email. You see it in SRTP for VoIP messaging. And you see it in things like IP security or IPsec. In these protocols, we're using the things that we talked about in the last module and implementing them. We may not see the math happen before our eyes, but we see the result of a secure communication. For example, going to YouTube, that is a secure site because it's using a certificate to encrypt the communication that you're seeing. You didn't need to see any of the math. You don't need to know how large the prime numbers are and the math that's being taken to do the private and public key exchange and all that. But you see the implementation. You see that the communication is encrypted from the rest. If you opened up Wireshark, you would see nothing but encrypted traffic. That is really what you need to be able to understand is the clear text versus the ciphertext, being able to see that by doing utilizing best practices, you can encrypt the communication that's happening to secure yourself or secure an organization as needed. Any questions? Okay. So let's stop this recording. Make a video. And then I'll go over what you need to do for your lab this week. So this will take a little bit. While it's working, did anyone have a chance to try the CTF 101 stuff or CTF Learn from last week? Ah, yes, Crypto Hack. What do you think? Okay. I know Crypto Hack has quite the interesting levels built in, and I believe they use a lot of Python. I do, but if I give any others, I'll give away what the answer is. I'm sure you could do the Crypto Hack in other languages, because in the end, you're trying to find a flag. But yeah, their aim was more to doing things in Python. But the tailgating question that not many have solved, I did see that somebody did solve it. Someone did figure it out. Yeah, I would say look at the Google mascot, and tailgating is kind of the big hint itself. When you see it, you're gonna laugh. Because it is a pretty silly answer. But yeah, well, a clue is the Googleplex and the word tailgating itself. All right, so that is done. Now let's make a new share of this. And proceed along. Okay. So your lab this week will be to connect to TryHackMe. TryHackMe is an online platform that you can practice quite a lot of training. Oops, that one's made private. In order to connect to it, you will need to connect to you need to make a VPN connection to them. So number one, you'll need to make an account, and you can make accounts for free. When you're there, go to the Open VPN room, which is linked. This one, I'll remove this one since that room's not available anymore. When you're there, it'll give you instructions on how to connect from your machine to their network. So if you are on a Windows box, here are the instructions on how to connect from Windows. If you are on a Mac, they have instructions here too. If you are on Linux as well. You are not going to be working on King of the Hill in this class. If you get a subscription, you can get a Kali Linux machine that's within their network already, and you wouldn't need to install OpenVPN to connect to their network. That part is completely up to you. I am in no way, shape, or form for this class forcing anybody to pay the subscription fee. You can if you want, and by doing that, you'll get a Kali Linux box that you can spin up and interact with the network directly, but you can totally connect freely by any one of these methods and connect their into their network. Once you're in, you'll do these two rooms, the Crypto Challenge and Crypto Funhouse, assuming they are up and running. Oh, that one's been made private. Has the other one made private too? Yes. Okay, so I'll double check that these links work, and you'll see what rooms you can work in. For right now, the first big step is signing up to try HackMe and making sure that you have a VPN connection to them. Once you have that ensured, then you can proceed to working on the rooms. An example of a room. Let's see if we can just type crypto. I'm just going to click on one randomly. Here's an example room. You'll have some tasks to do. So let's open this, for example. We have some terms here, okay? You can type in the answers if you have them for a question. And as you do, there'll be a little green check bar saying you did it correct, and you work through the various tasks to answer the questions to complete the room. You don't have to do as many crypto rooms. I'll pick 2 rooms that are publicly available, and you can work on those 2 rooms. This one looks like one that I might pick, this Crypto 101, but I'll update the links in the class. Instead of these 2, I'll pick 2 that are open. And what you'll do is go through each task, complete them, answer the question until you've completed the entire list of tasks to do. Now, if you choose to not do the 2 rooms that I picked, but instead pick 2 other rooms that are crypto related, go for it. I'm not going to force you to do 2 specific rooms. If you don't want to pick a room because you are completely unfamiliar with this platform, do the 2 that I'll suggest. If you see 2 rooms that are crypto based that spark your interest, go for it. The point of this week is to get you engaged with the Try Hack Me infrastructure and be able to do rooms within here, because this is a great learning platform that I believe anybody who's getting into cybersecurity should be familiar with. So once again, I'm going to suggest 2 rooms. I'll update Canvas with 2 rooms. If you would like to do those 2 rooms, go for it. If you want to do 2 other rooms that are crypto based, do that as well. Either way, you'll submit proof that you completed 2 cryptographic rooms within Try Hack Me. That's the main point of this week's lab. Does that make sense? Awesome. Any questions on this week? Okay. There are no questions. I will stop the live stream and the recording.